Hopefully, I'm live now. I'm gonna wait for someone to tell me that I'm actually working. Yeah. Okay. Let's make sure everything's working. Okay. Okay, soft. um, how do I get this to be? This is about as loud as I can speak. Uh, I think my mic is on like full already. How do I? Bruce, how do I adjust my volume? So slow. Okay. Uh, is like clarity okay, or is it just like the fact that the volume's a little bit soft? Okay, super slow. Yay. When should I start at 11 on the dot, or do we treat this like a lecture where I start at 11:05? Everything else is like here. Um, I might get started pretty soon. Might wait for like another minute or so just to see if anyone else shows up. But yeah, I don't know if there's anyone here outside of Bruce, but that's okay. Yeah, I'm just gonna be yapping for 2 hours straight. Let's go. All right, I'm gonna get bored, so I'm gonna get started. Hi guys, welcome to the Math3411 workshop from MathSoc. I'm Jessica Xu. I'm basically going to be covering us from for part one, which is going to be topics 1 to 3. And then Christian and Ronald are going to come in tomorrow for topics 4 to 7 at the same time. Right. Hope everyone's doing well and exam prep is going amazingly. But I'm just going to get started and jump straight into it. Alright, so just a reminder, I'm going to be going through the first 3 topics today. That's going to be a classic introduction, error detection and correction, and compression coding. Some of the content may seem a little bit basic, and like, we learned this a time ago, but I think it's very, very necessary. Plus, I threw in some exam questions so we can get an idea of what that difficulty looks like. Alright, I'm just going to get started then. So slow. Okay. So with our basic introduction, as we know, this course is about encoding, decoding messages and how we can play around with codes, right? So in here, we're just considering basic concepts like what is noise. Noise by definition is just anything during the transmission channel that can cause information to be corrupted. So for example, if I'm sending in a 1, or I'm sending in a 0 and it turns into a 1, then there was noise in the channel that corrupted that message. Right? Pretty simple, pretty slick. Okay. So, very, very quick definitions that I'm just going to throw in. Source alphabet. A source alphabet is seen as a set of symbols or words or anything like that, which build up all of the words that we need. Right? And they have associated with probability. So, for example, the probability of this symbol showing up is P1. And the intuition behind it you guys can think of as just like our English alphabet, right? So if I have like the word Thomas, you guys know, okay, it's comprised of THOMAS, and those are our symbols. And naturally, certain symbols are having a higher probability of showing up rather than others. So, for example, a letter like O or A might show up more than like a letter Q, right? So that's essentially the idea behind a source alphabet, right? And very, very similarly, we have a code alphabet. And the best example that I can think of here is just given here. So if you have a source alphabet of A, B, and C, which is things that we're trying to encode, and then the code alphabet is 0 and 1, then we can have a possible encoding that looks like this. So if I'm trying to code something like A, B, B, C, you guys will see that, oh, okay, A corresponds to 0, so that's just going to be 0. B corresponds to 1, 0, so that gives me 1, 0, and 1, 0 again. And then C is 1, 1. So super easy, this would be my encoding. Right? Super easy, super slay. Nice. I'm hoping that my audio is still going okay. Everything is still clear. If there is any point where the audio kind of starts to mess up or it gets a little confusing, please let me know in the chat. Yeah, so slay. And then this is just some of the prerequisite knowledge that Brits mentioned. So modular arithmetic covered in 1081 and other second year courses. Most important thing to note is just the concept of the division algorithm. But again, a lot of basic computations that we can do with mod in this course, we can do very easily using softwares like Python or Maple, MATLAB, anything like that. And yes, reminder that Brits very much encourages us to use code or anything like that to build our understandings. On top of that, we have probability, like binomial distribution and Bayes rule. But I think Thomas Brits did a really good job of showing us that we shouldn't really need to memorize Bayes rule because there's a very clear intuition behind it. And if you guys are unclear with the intuition, we're going to cover it later. Right? So, cool. Let's hop into a little bit more contents-heavy stuff. So let's talk about the ASCII code, right? So the 7-bit ASCII code is essentially where I have 7 bits, which refers to the amount of symbols, essentially. So for example, if I just make something up, that's 7 bits, right? Right? Yeah. I have 7 bits, that can correspond to anything like a symbol, or a letter, or anything like that. And then as I go through, that could correspond with different things. Right? So very, very clearly, it's a code. It encodes any symbol to a series of like binary letters. But how do we add a layer of like, well, error detecting, error correcting, something like that? And the way we do that is we have the 8-bit ASCII code. Right, so it's exactly the same as our 7-bit ASCII, except now we're adding an extra digit or an extra bit at the front. Right, so for example, let's consider this code 0110010. And what we usually do is we encode this so that it has an even parity, right? Even parity. So here you guys can see very, very clearly there are 3 ones. We have an odd parity here. But we want it to be even, so what are we going to do? Well, our check bit at the front is just going to be a 1. Yeah? And now if I look at this holistically, it has an even parity. Perfect. Super slay. However, if I had a very different code, so for example this is our 7-bit ASCII. If I wanted to add another check bit to make it an even parity, well, it's already even, so I just throw in an extra 0 at the front. Yeah, very simple, super slay. And that's essentially that concept there, right? So we give you an example of this, very much the same as what I just did above. So I won't go into it in a lot of detail, but you guys can see, okay, odd number, I need to balance it out with another odd, just so it becomes even, right? And this bottom here, right? The 8-bit ASCII burst code is just like, wait, what happened to the slides? Anyway, the 8-bit ASCII burst code is just like the extended ASCII, but with an extra row at the bottom, and that's referred to as the end of the transmission block, which basically acts as a little extra check, and it enables something else that I'll say in a second. Okay, if you're confused on what a burst code is, a burst code is essentially like if I had a series, is that 8? Yeah. If I had a code like this and I have burst, essentially what that means is a series of symbols might be a series of symbols in conjunction might all be corrupted. So for example, all three of these symbols might be corrupted just because they're in conjunction. And that would end up with something like this, right? Very, very big problem. And we're going to want to figure out how to correct that. So the way we correct it is using this block, this row at the bottom that is an extra check. And it does the same thing that we already were doing with our previous checks, where, for example, here, all of these zeros, okay, well, my check is going to be 0 to keep even parity. In this column in particular, we see, okay, this had an odd parity, so my check is obviously going to also be odd. And that is essentially the construction of this extra row, right? So before, if I say, let's take this example here. Well, we know that 1, 2, 3, 1, 2, 3, 4. We know that this is a valid ASCII, right? How do I know that it's valid? Well, it's 8 bits and it has an even parity. But if, say, something messed up and this got corrupted to 0, well then I can say, okay, well obviously some sort of error has occurred, and thus I know, okay, detecting one error. Why do I know that? Odd parity. Super slay. But the problem is with that is that I can only say, hey, I think an error has occurred. Some error has occurred. But I can't correct anything, right? I can't tell you, oh, well, it's this byte that's wrong. It's this byte that's wrong, right? I can just tell you that one of the bytes is wrong. One of the bits is wrong, right? So this is what this extra block essentially does for us, right? What it enables us to do is, let's say that this bit here gets corrupted and it goes to a 0, right? Something like that. And let's say that this gets corrupted to a 1, this gets corrupted to a 1. Well, then we can say very, very clearly, in our first row, it's invalid. Why? Because there are 5 ones, it's an odd parity, there's a problem here, not working, great. No, not great, but yeah. Then the initial instinct after that is going, well, let's check the columns then, right? This is absolutely fine. This is absolutely fine. You go through and you go, hey, hold on, there's an error with this one. This has an odd parity. So just by matching up the rows and columns, we can say, okay, this is initially a 0, it's wrong, so it has to be a 1. Under the condition that this is binary and radix 2, but yeah, this is going to be 1. And this is the same with these two, where you just go through and go, oh, okay, wait, hold on, it's the wrong parity, it should be the other one, right? And that ASCII burst, 8-bit ASCII burst code basically enables us to detect and correct up to 1 error, right? So slay. Oh my god, codes and ciphers! So slay. Okay. ISBN. So ISBN, a code word for uniquely denoting books, and then we have this condition here that all valid ISBNs must pertain to. I refer to this as a syndrome. So, for example, a sequence of numbers could be valid or invalid. And there is a very, very specific check to do that. So let's just go through I think I'll have more examples later, but let's just go through the very first one. How can I prove that this is a valid ISBN? Super good to say it, but like, how do I prove it, right? Well, if we just apply this equation up here, then I can go, okay, well, first digit, 1 times 0, plus 2 times 3, 3 times 8, 4 times 7, all the way, yada yada yada, all the way up to 10 times something, so it's going to be letters, numbers. 6 times 7, 7 times 8, 8 times 1. I'm so good at writing and speaking at the same time, guys. Yes, okay. Plus 10 times 7. Right, so essentially you guys can very clearly see, well, I have 1, 2, 3, 4, 5, 6, 7, and I'm just counting up. And then this is just all the numbers of that ISBN. And I'm going to actually get a number from that, whatever it is. And then when I mod that to 11, so hopefully I will get 0 mod 11. And if I don't get 0, if I get a random other number, then I know, okay, well, it's not a valid ISBN then, right? By definition. So I'm going to go through an actual example that we have here. Oh, JK. This allows us to do 2 error corrections, whether it's a wrong digit or an interchanging of 2 digits. Thomas Bruce did a really good proof of this. That's in our lecture notes as well. So if you guys want to take a look at that, please do, but I'm not too sure if that's exactly necessary. We just need to know that we can detect errors, right? But let's just go through a really basic final question. This is taken from the 2019 paper. It's not exactly the same question. The 2019 paper was like true or false, but hey, get the sequence, is it valid or not? And we're going to use the same method where it's just 1 times 0 plus 2 times 9 plus 3 times 0, yada 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 yada. Right? And I'm just going to scroll down to our solution here. And if anyone has any questions, please let me know. But scrolling down to our solution, we see that we end up getting 208 as our final sum. And naturally, 208 mod 11 is not congruent to 0, so hence not valid, right? Super easy, super slay. But I want to extend this exam question a little bit. I think this exam question, pretty basic, pretty simple. So let's just go, okay, well then how can we make this a valid ISBN, essentially, right? So let's, sorry about that. Oh my god. Okay, sorry about that. How can we correct one of the digits here to make it valid? So what if I told you, okay, the last digit is the one that has an error, okay? If the last digit is the one that has the error, please correct it so that it is the correct number instead of 4, right? So, okay, how would we make this valid? Well, I'm going to do the working out here. Okay, going through this working out here, you guys can already really easily see that the sum of the first 9 numbers, so the sum of these 9, would just be, if I had I equals 1 up to 9, I is going to equal to 208 minus 40, right? Because I'm just minusing that last term there. And that's going to leave me with 168. And considering the equation again, we're going to go 168 plus 10x 10. And that's going to somehow be congruent to 0 mod 11, right? And you guys can use code for this, you guys can use your just handheld calculators, you can use your brain, but what you'll end up getting is that the final digit should be, I think, 3, right? And then that will leave us with our valid ISBN. Naturally, this working out would change if we didn't know that the 10th digit was the one that was wrong. So if it was like the 2nd digit that was wrong, or the 5th digit, the working out would naturally shift for that, right? But super slay, and that is the end of our introduction. So hopefully that's all good, and if anyone has any questions, please pop them into the chat. But otherwise, I'm going to jump straight into chapter 2. Alright, so slay. So error detection and correction. So we had some basic examples with the ISBN and ASCII codes, but let's extend this to a bigger mathematical framework, right? So just the idea of this chapter, it's focusing on the concept of noise that I was talking about earlier, right? And for example, if there is noise in the channel and I have a probability P where it gets corrupted, then naturally we can craft this as a table to represent that. Not table, diagram? Yeah. Diagram to represent that, right? So, okay. Yeah. So we're basically looking to detect and correct errors. So slay. Right. Binary repetition codes. If no one remembers this, this is the part where Thomas Fritz in the lectures was just screaming hello a lot of the time. So if I want to put in a code word hello, and I wanted to make sure that my message comes through as clearly as I possibly could, then I would just, the easiest way to do it is just repeat it, right? So if I go hello, 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 and for some reason on the last one, there's just a small error, right? Well then most likely my message is hello, right? And that's basically the concept of binary repetition. This idea where if you just repeat your message a bunch, then it's going to somewhat come through with a certain level of probability with it being correct. The reason why this is not necessarily the best, which we will cover later, is because it's not as efficient, right? What's the difference between this and repeating 1,000,000 times, or 2 times, or just not repeating at all, right? So it's just making sure that our codes are efficient as possible as well. But binary repetition codes, where you simply just repeat, right? So there's a lot of different strategies to detect and correct codes for binary repetition. But naturally, if I have the message 0, and I have it as a 5-bit binary repetition, then it's going to become 5 zeros. Very easy. Same with the ones. Yeah? And I can tell very much, if I get 0001, well then that's not actually one of these code words. However, we can detect, I there's probably an error here, right? And we can try to correct it using a couple different strategies. So let's talk about those strategies. The very first one that I'm going to mention, where is it? Okay, cool. Don't know what happened there. Is you can correct up to one error. So essentially, if I'm saying that these are my code words, these are my valid code words, and I get 0001, I can say, oh, okay, well, we can see that probably one error has happened, and this one is probably a 0 that got corrupted. So then I would say, okay, well, let's make that a 0 then, right? And then same with this code word here. We can just convert this 1 into this 0 into a 1, right? And same with this even side, we can convert. And that's basically strategy 1. Correct up to one error, and then we're going to call everything else just invalid. We don't know what that is. What is that? That's just wrong. Cool. Second strategy is correct up to 2 errors, where, again, you can still very, very similarly do these code words, but now you can also extend it to these code words, right? And that's very much turning these into 0s, turning these into 1s, same with the other side. Hopefully everything's good there. And the last strategy is just absolutely no correction. If I get anything outside of this, then it's just wrong. Right? Kind of funny. Okay. But now I just really want to consider why can we not correct more than 2 errors? So I can correct up to 1, up to 2. Why can't I correct up to 3 or 4? Right? And the reason why is, let's just consider the ambiguity of up to 3. If I was just to look at the odd side real quick, say I could correct up to 3, right? Then let's just look at this example. Up to 3 means I can also still correct it if it's just 2. So I could interpret this as, hey, it's likely just a bunch of 0s. Or alternatively, if I can say it's up to 3, then I can say, oh, okay, it was this sequence that was wrong. And then I can interpret it as this. And because I have multiple interpretations, correcting up to 3 doesn't really do anything for me because I'm still left in an ambiguous state, right? This very, very similar logic applies to this example here, where you just don't know if you want to correct the 0s or 1s, and hence, because of that ambiguity, we just leave it, right? So you can't correct more than 2 in this example. And Thomas Brits does a very good generalization that we're going to cover again later, but that generalization is just that for odd and even fixed length codes where they can be represented in terms of t here, then we can correct up to t errors. Right, for binary repetition codes. Okay, so slide. Hopefully that is understood. Okay, again, please, if anyone has any questions, I'd love to interact with people. Please don't be shy. So slay. Okay, binary Hamming codes. So a binary Hamming code is a code of length n with k information bits. So if I have just n where I have k information bits, then actually the alternative is I have n minus k check bits, right? Check bits. And the condition for a binary Hamming code is a single error correcting, and it has that parity check matrix, right? And that's determined by this size. I also love binary Hamming codes. Okay, but yeah, a lot of you guys would remember this as like one of our not one of our primary questions, but it was definitely a question in our lab test 1, right? And the condition for this matrix is that the matrix times by any code word is going to end up with the 0 vector. That is the idea of the parity check matrix, right? And you will see this in practice in a second. So, first things first. A common example is the Hamming 7.4 code. Another example that you would have seen in our tutorial questions is something like the Hamming 1511 code, where we have basically just this, right? And my question is, why is it 7.4? Why is it not 6.4 or 5.4 or something else, right? And essentially the idea is we want to make sure that it is always going to be single error correcting and has that parity check matrix, right? And while 6.4 is not impossible, it is possible to write a code like this. If you do write a code with this though, it will not satisfy these conditions. That is just essentially the error. And an equation that you can think of just to help you out is something that looks like this. So 2 to the power of the number of check bits. In this case it would be r, but I'm just going to use 2 because it's binary. Minus 1 has to be greater than or equal to n. Right? So if I had 6.4, then the number of check bits is, again, 6 minus 4, so that's just 2. 2 to the power of 2 minus 1 has to be greater than or equal to 6. And actually, you guys can see that this is not true, right? But the second it's 7 and I have 3 check bits, then this condition is held true. It works. It's going to be single error correcting and have a parity check matrix, right? So this is a very, very good equation. Just to keep at the back of your head. Okay, and I've written that out here. Essentially the same thing that I've just said, right? Okay. So Hamming 7-4 code. Right, still given here, but a property of the Hamming codes is just the dependent columns are positions of the information bits. The independent columns are positions of the check bits. Right, and the intuition behind it is essentially that we always want a unique code or a unique interpretation of every code word. So in that, we want our check bits to be unique for every single code word. It can't be any ambiguity. It can't be any alternative way. And for that to happen, it has to be our independent columns, right? It can't be dependent on the information. So it's like, yeah, by design. Yeah, just our answer given there. Just in case you didn't catch exactly what I said. Yeah, this is by design. Okay, so how can we actually use this to correct errors? Because that's the whole point of the topic, right? How do we use this to detect and correct errors? So suppose that we wish to send in code word X, right? And we receive Y instead. Well, we already know. If I had this, well, if it's correct, if it's valid, it would equal to 0, right? Because that's what we defined Hamming codes earlier as. It has to equal to the 0 vector. However, if it doesn't equal to the 0 vector, then we can say, oh, okay, we have detected that an error has occurred. And the way we correct it is we just check which column the resulting vector corresponds to, right? So let's say for the Hamming 7-4 code, if I did HY transpose, then, and I, instead of getting the 0 vector, I get like 110, and then we would say, okay, well, 110, that corresponds with the third column, so our third bit is wrong. We're just checking the comparisons with the columns, right? And we'll go through an example of that. So, non-exam question. Suppose we are using the binary Hamming 7-4 code. We receive the following message, blah, blah, blah. Correct the encoded message and determine what the information is, right? So do I have... Yes, I do. Okay. This should be a Y transpose. My bad. Yes. So this is the Hamming 7-4 code, as I've kind of thrown on this page for a while now. And I'm just writing the message, transposing it, and calling that our Y, because that's our message, right? And naturally, in congruence with our syndrome, we want to find the matrix multiplication of these, which you guys can throw into anything, any program, any software that you could possibly want, but you end up gonna get 0, 0, 1, right? And naturally, woo, alarms going off, this is not the 0 vector, an error has occurred, right? And we can say, oh, okay, this is actually the same as our this column is the same as our 4th column. Hence, there is a problem with the 4th bit. And then we just correct that. So we go, instead of 1, 0, 1, 1, 1, 0, 1, holy crap, okay. The 4th bit has a problem, the 4th bit is 1. If it's wrong, then it has to be 0 in radix 2, right? 1, 0, 1. Pretty simple, pretty slay. And, oh, the final part of the question is to determine what the information is, right? So I'm trying to do this without looking at the answers, but you guys can see these 3 columns here are our independent columns, right? And then these up here, maybe I'll just delete this for the sake of ease. These here are our dependent. And our information, if you guys remember correctly, is in our independent columns. So I'm looking at the 3rd bit and then the last 3 bits. And that's going to end up with us having 1, 1, 0, 1. Yeah, so slow. And that would be our final answer there. Right? Super cool. And I just want to go through an example of a exam question. So exam question, check whether a random string of 15 ones and zeros has a 1 in 16 chance of being a code word in the binary Hamming 1511 code. Right? So again, binary 1511 code, what do I know immediately from that? Well, I know that I have 11 information bits and then I have 4 check bits, right? By definition, right? So the position of these information bits doesn't really matter to me. The position of these check bits doesn't actually really matter to me for the sake of this question. What does matter to me is if these check bits, if they're a 1 or a 0, right? So if it's going to be a 1 or a 0, then we can say, okay, there's half, 1 and 2 of it being the correct, it being the correct value, right? And if I have 4 of these, well then naturally I can just times itself by 4, right? So that is for all 4 check bits, and that's going to end up with 1 on 16. And if you're curious, this is what the working out would look more decently like written down. There was no need to know the having 1511 code, but naturally because it's easy to like search for, it's easy to find, you could have also used this to find your answer, but I don't feel that knowing the positions was exactly very necessary, and there was other ways to do it, right? 2 different methods, both equally as valid. Super slay. How are we doing? How's everyone? How's y'all's day going? Hopefully good. Okay. A very final remark about binary Hamming codes is that as my information bits increase, as the number of information that passes through comes through, naturally we'll need less check bits, but our information rate gets closer and closer to 1, right? If you guys are curious on what on earth information rate is, we're going to cover it very, very soon, but the idea is, great, the information rate is closer to 1, but we're always going to be limited to the fact that it can only ever correct 1 error, and that's it. So slay. Okay, Hamming distance and weights, and this is something that we need to know contextually as like jargon, but like I feel like all of us have been using this concept implicitly at least, right? So the example that I want to use for the implicit, how we've been almost using this implicitly, up here, great. Up here, when we're talking about correcting up to 1 error or 2 errors, we could have easily said, okay, well, this only differs to the original code word by 1, right? The only difference was that one final last bit there. So hence I could correct up to 1 error. Same with the second one, I could say, okay, it has a difference of 2, and same with here, I could say that has a difference of 1 as well. And that's essentially the idea of those distances. So if I could scroll back to where I was at, yep, here. The distance is just the number of bits that differ, right? So if I had, say, this and this, well, we can see, okay, first bits of them are the exact same, second bit is different, so I add 1, third bit is different, add 2, okay. And the last 2 bits are the exactly same. So the distance between these 2 is 2, right? And in a set of code words, how this comes through is that the minimum distance is the smallest distance between any pair of code words, right? Obviously, the code words can't be the exact same, just a pair of code words, right? A very, very similar concept is Hamming weight. So Hamming weight is essentially just where it is not 0. So, for example, if I look at something like this, well then I can see that 3 bits of this is 1, so it has a Hamming weight of 3. Minimum distance is naturally where, in a set of code words, what is the closest to being fully zeros, right? And by how much? Super slay. We don't put it in this seminar exactly, but just a reminder that Thomas Pritz went through a really interesting proof of the relationship between distance and weight, and it is probably worthwhile to go back and check on that. Yes. Anyway, minimum distance decoding, denote D as the minimum distance. We can have a strategy called minimum distance decoding. That was essentially what we were talking about earlier when we were talking about strategies, and the central concept behind that is, for example, if I had, say, a timeline from zeros, let's say just say like 5, and then a set of 1s, right? Well, we can say somewhere on the spectrum is going to be whatever code word we have, whether it's invalid or valid, right? So for example, this means no ambiguity. This has no meaning in terms of the actual space. I do not draw things in scale, but let's say we had a code that's like this. Well, naturally, because it's closer to our zeros, we can say, okay, we're going to correct it to be 0, right? A bunch of zeros. And the reason why we could say that it was closer is because the distance between these two was just 2, but the distance between these is 3. And it's just simply closer to the bunch of zeros, right? And we can do this with any code. So if I had one that just has 1 difference, then that's that. If I had one that was just closer to our 1, same thing, right? But the minimum distance decoding strategy essentially just takes into account how different it is to the valid code words, right? And again, that's going up to our same ideas from earlier. Yep. Cool. Oh, whoa, what happened here? Okay, hold on. I have an example for this. I have an example for error correcting, and I think it just messed up in terms of the slides, but I have the paper somewhere. Yeah, there it is. Cool. Which example is it? Is it not this paper? Am I tripping? Is this not 2019? Oh. Apologies, give me 1 second. I do want to do the question, so give me 1 second to just very, very quickly find it. Okay, it is not this paper. I've been absolutely lying to myself. This is so sad. 3 IB. 2018 is my guess. Yeah, okay, so Sly. Found it! Oh my god, it was only the last one that I checked. Okay, so hopefully everyone can see this. Hopefully that oh, luckily I had that paper up. Okay, but so Sly. Essentially, this is going back to the concept of error detecting and error correcting that we've been discussing this entire time, right? And let's just talk through it. An error correcting code C is defined for integers greater than or equal to n, greater than or equal to 3. Each message is blocked out like this, like this, okay, and then they form a cube, right? And then basically the central idea is explain why the code is to error correcting, right? Super easy, super slay. But let's just think about this through a simpler lens first. Let's look at this. Instead of it being 3D like a cube, let's consider the 2D plane first, right? So if I just had a set of random, I'm not going to do 7-bit ASCII just because it's a lot of numbers for me to make up right now, but let's just have this, right? Oh, maybe I should make this an actual like square because the question calls for a square or a cube. 1 1 0 1 1 1 1 1. Sure. All right. And then I'd have check bits around this. This is accurate. Yeah. Okay. Not completely like check bit safe, but like yeah. If I say had this as my set of code words here, so I have 4 code words, each of 4 bits, then everything around it is a check bit, right? And I can essentially just go, hey, is this row okay? Yes or no? Yes, it is valid. This is invalid, so there's an error here. I am missing a number here. Is this invalid or valid? This is valid. This is invalid as well. And this is going to be valid, right? So that's just me going through the rows. And if I go in through the columns as well, then I would say, okay, this is valid, this is valid, this is valid, 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 right? Ooh, I want to make it so that one of these are invalid at least. Let's make it this one, right? So suddenly the second one is invalid, and let's say this is also invalid, right? So, okay, I have 2 rows and 2 columns where there is a problem here. The reason why I cannot correct 2 errors when there is naturally probably 2 errors here is which 2 places is that error occurring, right? Sorry if this is super, super confusing. If it is, please let me know. But, for example, what if the error was here and here, right? Or alternatively, it could be here and here, right? Or who knows, it could be somewhere completely different and it just messes everything up. But because there's an ambiguity in the positions, or it could be either one of these, then we can't correct it. However, we've just proven, okay, on a 2D, if our encoding can be represented on the 2D plane, it cannot be 2 error correcting. However, if I was to just fix this up a little bit, let's say this is 0 and 1 so that this actually works. Yep, everything works. Then, what is happening? Yep, this is supposed to be 0. Okay, then I can say, alright, well there's an error in this column, there's an error in this row, so I can just realize that, hey, it's probably this bit that's wrong. And then I can correct one error, right? So on the very easy 2D plane, we can determine that it is one error correcting, right? Super slay. But now let's actually answer the question, and let's talk about this instead. So we have a 3D plane here. We have a message that can be encoded through a cube with n-1 layers, and the check bits form the n cubed. So hopefully you guys can see where I was trying to get through with the 2D example. But essentially here, they give us an example of what it's like to encode a message. Very, very helpful. But essentially, if you guys are a little bit confused on where these numbers come from, it's 0, 1, 1, 0, and then we're looking at this side, so 1, 0, 0, 1, right? Just to help us understand how the encoding works a little bit further, right? So explain why the code C is 2 error correcting. Well, in the 2D example, you guys could very easily see, okay, well, if there's if there's an error in one column and there's an error in one row, then it's going to be that one space. And if we extend that to the 3-dimensional plane, well, then naturally we can break it up and rotate. This is very hard to illustrate. Yeah. And it would look something like this as well here. Very hard to illustrate. But essentially we can rotate the cube in such a way that only one row, one column can be found. So we rotate it around until we look at every single row and column. We break it up, and then from that we'll be able to find 2 errors, right? So if I were to say that out in a bit of a nicer way, if there is at most 2 errors, so if at most 2 errors, we could rotate the cube. We can rotate the cube such that a layer has only 1 error. Such that a layer has only one error. The reason why this doesn't work for 3 errors, 4 errors, or anything more than that is because from then on, there is no way to rotate it so that each layer only has at most 1. There would be a layer that has 2 or something ambiguous or strange like that, right? Moving on. State the minimal value of t for which C can always detect up to t errors, right? So, okay. Assuming the pure error detection strategy, so this is in reference to the strategies that we were talking about earlier, but assuming the pure error detection strategy, I did not space that out correctly, is actually going to end up being 7. And the reason why is we can think about it conceptually. If we just think about how we would detect 8, right? Could we detect 8 errors? And the easiest way to show that we actually can't is if I had, say, a cube. Ooh, this is so poorly drawn. I am so sorry. Is this the time to say that I am not an artist? Haha, classic math teacher joke. Anyway, sorry. Okay. In particular, if we had 8 errors, and for example, they all occurred in like the corner of the box, something like this, then we would actually have no idea that happened, right? We would have no clue that happened. And this is simply using pure error detection strategy, not anything. Oh, this is the missing word, detection. So true. But yeah, if I had 8 errors happening and they all formed the corners of the box, then I would simply not be able to detect anything. I would simply just think that it was correct, right? But it's very, very easy to see, hey, if one of these was just like fine, if this was right, this is just clear, then I would still be able to say an error has occurred. It's either going to be 1 or 7, but I can still see it's up to 7, right? But the second it goes past 8, leads to problems, right? And that is basically that question there. Pretty long, pretty intimidating, but not too bad. Hopefully everyone understands that. Hopefully I didn't just drop someone there. Yeah. Let's go back to these messy slides. Yes, this was me just trying to put in the images for those. Okay, so sphere packing condition, right? Hopefully everyone's okay. Just checking that everyone is like still kind of following. Okay, sphere packing conditions. So let's talk a little bit about this. So we have naturally this theorem here. Very much, what is that? So let's talk a little bit about the intuition behind it. And it uses the concept of minimum distance that we were talking about earlier. But r to the power of n, where r is the radix, r to the power of n is just going to be any possible code word. Whether or not it's valid or not doesn't matter. But r to the power of n signifies the amount of possible code words we can have, right? And here, that's just going to be our cardinality, so the number of valid code words that there are. But now we just have to address, what on earth is this, right? So let's say I have some ambiguous random field. Pretend that joins together well. Some ambiguous random field. And in this field, there is r to the power of n code words, right? Because it's all the valid possible code words that I could possibly have. But within this field, I only have a few valid code words, right? So let's say code word 1, code word 2, like code word 3, whatever it is. Alright, so in this case, this cardinality here would be 3, because there's 3 valid code words. But let's say I wanted to be able to detect, like, to correct one error, where t is equal to 1, right? Well, then it causes a little space within this that I can correct up to, right? And naturally, this is going to be a circle because if it's one error, it's one radius, right? And naturally, as this increases, so if it's not 1, if it's like 2, then this space where it is able to correct increases, right? And you can see that like, no matter how large this gets, we can never find code words that are outside of this area. So hence why we have that inequality here. It always has to be less than or equal to, right? But moving on, this is essentially the concept behind this, right? Where we consider radix and the number of possible sums. But that leaves us with this combinatoric here. How does combinatorics come into play? Well, so for example, if I had a string of 5 bits, 1, 2, 3, 4, 5, for example this, and I said there are 2 errors here, well then very easily we can say that there are 5 choose 2 places where that error could exist, and hence the role of combinatorics in this, right? Again, sphere packing is something that's also pretty easy to code up. Okay. Binary linear codes. So, oh my god, give me a second. Okay. It is essentially a generalization of Hamming codes as shown previously, and we're going to be working with this generalization. Yeah, okay. So the minimum distance for linear codes, very much what we were working with earlier, where we were talking about linear dependency, and let's work with this non-exam question to uncover what we're trying to say, essentially. So the non-exam question, suppose that we have a binary linear code with this given parity check matrix, and we receive a certain message. Well, parity check matrix, I already know instinctually, what am I going to do? I'm going to find this. I'm going to see if it's equal to 0, right? So, okay, when I put that in, I'm just going to put transpose of this, yt, and then I can use any software that I possibly want, do this in my head, whatever it is, where I find the matrix multiplication, right? And that's going to end up with this, right? 0, 0, 0, 1, cool. Where I have mod 2. Okay. And we can all agree that, hey, this here doesn't actually perfectly line up with any of these columns. So the method that we were using earlier doesn't work here. However, what we can say is because it's mod 2, I can say that this is equivalent to this, right? Too many zeros. Right? Just because 2 is congruent to 0 in mod 2, right? And hence, this is a construction between 1001 and 1000. which is our first and last columns, right? And hence I can say that there is an error in our first and last bits. So if there's an error in our first and last bit and it's originally 10001, then naturally I can correct this to be a bunch of zeros. And if I was to find the information, well, then we can very clearly see that 4 of these are linearly dependent. So like these 4 are linearly independent or independent columns. And then one of these is not. So one of these are dependent on the other. So the information is just going to be one of these bits, which is 0. Right? Super slay. Hope we're going well. Okay. Okay. So let's actually talk about a exam question, right? So binary linear code has a given parity matrix. Find the probability that all errors all errors are corrected correctly when using the minimum distance decoding strategy, right? So what am I going to do? Okay, well, I can see that there are going to be I can see that I can work with linear dependency and linear independency, right? Because we're working with linear combinations here. So essentially, what am I going to be trying to do? I'm going to go, okay, well, obviously, all of these columns by themselves are going to be linearly independent. However, what about if I had pairs? Well, same, this is going to be linearly independent. Same with here, linearly independent. But the second I take all 4 columns, you can see that this column can be a construction of the other 3. Hence, we're going to be talking about the smallest set of columns that are linearly dependent is 4, right? And if we were to write this in the same form as we were writing out even and odd fixed length codes, then I'll say 4 equals to 2t plus 2, where t equals to 2. Oh, t equals 1. Get pranked, lol. And by the minimum distance decoding strategy, we can only correct up to 1 error, right? So if we can only correct up to 1 error, then that probability is going to be, using probability, is going to be 4p1 minus p cubed, right? Super slay, super easy. So find the probability of detecting at least 1 error when using the pure error detecting strategy, right? We can think of this in 2 different ways. We can think of this as, well, okay, if it's at least 1 error, then there is going to be either 1 error, 2 errors, or 3 errors, right? And then we can just add those 3 errors. Yep. And then we can just add all of those probabilities together, right? Alternatively, the other way that we can think about it is just 1 minus the probability of 0 errors or the probability of 4 errors, right? Both valid ways to think about it. But a written solution of that would look something like this, right? If anyone has any questions about this, please, again, let me know. Super vibe, super slay. Alright. Okay. Moving on to generator matrices. So before we were talking about parity check matrices, and it was just a way for us to display code words through a matrix, right? And in that parity check matrix, just a reminder that it was based around this definition, right? That any valid message, when multiplied with the parity check matrix, would give us the 0 vector. That was the definition for the parity check matrix. And the generator matrices is just a different way to represent this. So instead of having this syndrome, what we're essentially saying is that every row in the generator matrix is a basis for every single code word, right? So if I had like, let's say this, right? Then I would say that the bases are 1001 and 0101. And from that, my code word is going to be any linear combination of these guys, right? Super slay. I know that that's kind of hard to visualize right now, but we're going to go through some examples. But before that, standard form matrices. So we know generator matrices, we know parity check matrices, and they're both valid interpretations or depictions of how a code word can be defined or created. So if I have multiple interpretations, instinctually as mathematicians, we just go, oh, how can we form a relationship between these two, right? And this is essentially that, where we basically define it using the identity matrix. So if our matrix, so for example, 1 1 0 0 0 0, let's just say some random letters here, or symbols here. If we can arrive at this by row reducing or permutations or anything like that, then we can very easily kind of convert between the two. And that conversion is defined here, where, oh my god, okay, where if you can represent it with the identity matrix and some other, then to convert to the generator matrices, we just basically flip B and the identity matrix, throw a negative in front of it, transpose it, right? Oh my gosh, give me a second, I'm gonna drink some water. Holy crap, okay. Okay. Okay, sure, very nice break. Okay, that's basically our conversion there, and we'll go through an example of that basically right now, I think. Yeah. So from our 2017 paper, we're going to be trying to find a basis for C. And instinctually when I look at this, I go, hey, hold on a minute. The very first 3 columns is our identity matrix. Oh my god, this makes my conversion so easy. So what this ends up being is if I'm to flip it around and I go, hey, let's follow this. I need to flip this, transpose it. So if I transpose it, it's going to be 1 0 1 1 0 1. And the end is going to be our identity matrix, right? So then I have 1 1 0 0, right? And this essentially becomes our generator matrix. And by definition of the generator matrix, the basis for C is just going to be the rows of this matrix, right? So our basis is going to essentially be all of our rows. 0 1 1 0 1. And that's our basis, right? And that's our answer there. Super amazing, super slay. Cool. Hopefully everyone's doing okay with that. Just before I go into what it means to add higher radii outside too. Yeah, okay. I know that a lot of what we've been doing so far has been under the assumption that it's binary, like radix 2. Basically now we're going to be talking about what it means to extend it beyond 2 and go to a higher radii, right? Like what if it was radii 2, what if it was radii 3, 4, 10, million, whatever, right? And we're going to be going through this through basically the lens of ternary. So there's some added complexities to it, and this is basically the end of our topic too, but there are some added complexities to it. And the idea here is just that, first of all, naturally our matrices and our matrix computations becomes a little bit more complex because we have entries more than just 0 and 1, right? And on top of that, this conversion that we defined here, where is it? Oh my god, okay. This conversion that we defined here is no longer actually valid. Oh my god. Okay. This conversion here is no longer actually valid. And the reason why it was valid in the first place is when we just took away the 0, when we just added the minus at the front again, this was under the, this was in correspondence with the fact that, like, for example, -1 is equivalent to 1 in mod 2, right? But naturally, this is not the same case if I increase this radii, right? So hence, this conversion isn't going to work anymore. Alright, and that's basically our added complexities there. It is also more difficult to identify linear combinations, but, yeah. Ooh, whoa, okay. Alright, so that's that. That is topic 2. I would say very, very main key takeaways is our generator matrices, parity check matrices, Hamming codes, stuff like that, and our detection strategies. Basically a very quick TLDR, what was this topic? Correct codes. Yes, super slow. Alright, I'm gonna take another sip of water, because my throat is a little bit dying, guys, before we hop into topic 3. Okay. Jesus. Okay. Let's go on to topic 3, compression coding. So I kind of alluded to this earlier, and compression coding is where we're essentially looking at the idea of efficiency. How good is the code, right? And, okay, yeah. In the previous section, we only dealt with fixed length codes, which had a focus of error detection and correction. Reminder that fixed length codes mean that every single code word in this has a very fixed length. Very intuitive, very understandable. But suddenly, what if we could make it so that it wasn't fixed length? What if we could decrease the length to be more efficient and still have the same effect, right? That's essentially the purpose of this topic. So, yep, this chapter was efficiency. How can we decrease code lengths while still keeping the same information? And here, we're assuming that there are no errors, right? So we've already dealt with all about error detecting, all about error correcting in the previous topic. In this topic, we're basically assuming that it's all good. Like, there are no errors, we're just going to be working with what we got, right? To do this, we need to know a little bit more about the source symbols, and in particular, their probabilities. So remember that earlier how we were talking about this was a symbol may have a certain probability of showing up, right? And the example that I gave at the very beginning of the seminar was like, oh, okay, symbols like A or any vowel or something is going to show up more in common than like symbols like Q, right? That's that probability that we need to know. And for this section, we're going to be using like these definitions. Source is S, code C, P is probabilities, L is like very much in congruence with our lecture slides, right? But let's go through some very, very basic definitions. First of all, uniquely decodable codes, right? To be uniquely decodable, there is only one way to interpret a message, right? And I think I have, oh, okay, we'll talk about it later. Instantaneous codes. Instantaneous is very much an easy definition, and it's also very easy to see, but if the code word is a prefix of another, then it is not instantaneous. Cool, let's go through some examples here. So, this is the standard comma code, and the standard comma code is essentially defined by zeros, where if I go S2 or S3 or S4 or if I had to go even further over length, let's say 4, if I went to length 4, then naturally still goes to this, 1, 2, 3, 0, 1, 1, 1, 1, right? The standard comma code is defined by its zeros, essentially. You guys can very, very clearly see that this is obviously instantaneous, just because this is not a prefix of any other code word. Same with 1, 0, 1, 1, 0, same as all of that, right? And it's also uniquely decodable. How we know that it's uniquely decodable is that when we're decoding, we're just going to be looking after the zeros and where they are, right? There is only basically one way to interpret this, and it's just to stop at every, oh my gosh. It's just to stop at every 0, right? So there's a 0 here, okay, it's at the third bit, this is S3. This is the very first bit, so it's S1, right? Oh no, the next 3, because I know it's length 3, the next 3 has no 0, so it's S4, right? Just looking at the zeros and finding that. So that's why it's uniquely decodable, right? However, let's consider this code. First of all, is this code, let's do the easier one to see, which I think is instantaneous because I'm just looking at the prefixes. Is this instantaneous? Well, immediately I can be like, no. The reason why is because S1 is a prefix of S3, right? You see those zeros. Hence, it is not instantaneous. Is it uniquely decodable? Very quickly, I can also say that it is not uniquely decodable, and the code word that I might, the message that I might consider for that is something like 0110. Oh my gosh, too many zeros and ones. Anyway, 0110. You guys can easily see that this can be interpreted as 0 and 110, which is going to be S1 and then S2. Alternatively, 0110 can be interpreted as 011 and then 0, and that's going to be our S3 and S1. And because this same code word has two interpretations, two ambiguous interpretations, it is not uniquely decodable. Very easy. So, not instantaneous, not uniquely decodable. And I think that's written down here. Super slay. I'm basically pausing on these just in case anyone doesn't exactly catch everything that I say and you guys just want to pause. What did she just say? What is the song? Okay. Let's consider another code. So considering this code, very quickly, we can say that this is not instantaneous, right? Because this 0 prefixes every other code word. Not instantaneous. However, is this uniquely decodable? Very interesting question, right? What I I can say is, okay, well, it actually is uniquely decodable. And how I can quickly determine that is, it actually is very, very similar to our standard comma code, if you guys remember that. Except now we're just reading right to left. So for example, if I was reading right to left, you guys would see this, right? And this is very, very much reminiscent of our standard comma code, and hence uniquely decodable, right? So if I was to decode using this code, I just read right to left, which I think is written over here as well. So it's not instantaneous, but it is uniquely decodable. So slide. Yeah, and then there's a key takeaway here. All instantaneous codes are uniquely decodable, but not all uniquely decodable codes are instantaneous. Super slay. Okay, if we have an instantaneous code, then decoding is really, really easy. We just start reading from the left and stop every time we have a code word, right? And repeat on and on for essentially forever, right? So let's go through that as a really, really quick example. I think it's worthwhile to go through this, not like just to run past it, but just to go through it really quickly. Obviously, 0 is not reminiscent of any code word. So we go on, we move on. What about 0, 0? Okay, I can see that that is S2, right? And then that's those two are the same. 1, is that a code word? Yes, it is S1. Okay, moving on from that then. 0, is that a code word? No, but it's 0, 1, yes. And then you essentially do that on and on and on until you reach the end, which is going to end up with S3, S3, S2, S1, right? 2, 1, 3, 3, yeah. And that's this deconstruction here, right? Very, very clear. Pretty, I feel like, easy, I guess, to say. But that's just that simple decoding using instantaneous codes, right? Okay. Kraft-McMillan theorem. Oh my god. Super, super important theorem to know. And Thomas Briss has definitely told us that we need to know this kind of stuff. But Kraft-McMillan theorem. These statements that I'm going to say here are essentially equivalent, right? So, yada, 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 yada. Great. Cool. Radix R, UD code with code length blah. Radix R, instantaneous code. And then this very, very funny sum here. Alright, and I'm just going to show you this code here. So, this last dot point here is essentially the measure of efficiency. And that's in terms of like information rate that we're going to talk about, I think, later. But it basically talks to us about how compact or how efficient the code words are. And we'll be using this equation to basically show whether or not a certain code with certain lengths can exist, right? Which you guys should remember from the lab tests as well. But, for example, there is no radix to uniquely decodable code with these given code words. And the reason why we know that is because if we sub these lengths into this equation, we're going to end up with 1 on 2, 1 on 2 squared, and 1 on 2 cubed. And that's going to end up with 9 on 8, which is greater than 1. And hence, because it is not less than or equal to 1, then it is there is no code that exists with that, right? Very easy, very, very quick check. Okay. An example of this that you guys can kind of do is there a radix 3 instantaneous code with these given lengths? And if so, construct that instantaneous code, right? So let's just do a really, really quick check, right? Using this, oh my gosh, my throat is so not okay today. That's not slay. Okay. I'm just writing this out again. Writing out a third dot point, this is the sum that we're trying to look for. And if I was to put in all of these code words, then I would go, okay, 1 on 3 to the power of 1, 1 on 3 to the power of 1, 3 to the 2, and then there are 4 of these, so let's just say 4 on 3 to the power of 3. Yep, so that's like. And then if you were actually to compute this out, you would get, I think, 25 on 27. Yep. And because it's 25 on 27, that's going to be less than 1. Therefore, it exists. It exists. Right? And now our next job is to actually construct the code. Right? And the way that we can do this is there are actually 2 methods that I know of, but they're very much the same thing. The very first method is essentially using Thomas Britt's method where he just basically constructs like a tree. So if I go radix 3, then I go, okay, this is my starting point. Radix 3 means I can have 0, 1, and 2, but if I have a 0, that's going to be my code word of length 1. right? 1, that's going to be my code word length 1, and 2. And I'm actually going to continue branching off of 2 because I need code words that are more than length 1 now. I feel like I need more space for this. So let's see if I can just move everything over a little bit. Okay. Going from 2, again, I can have radix where I add on another 0, because it's radix 3. And that's going to be my code word length 2, because it's 2, 0. Similarly, I have 1, but I don't need another one with length 2, I need one of length 3. So I just add another branch, essentially. 0, 1, and 2. And then these are going to be 3 ones where I just have length 3, because that's 2, 1, 0, 2, 1, 1, 2, 1, 2. And then, funnily enough, I still have one more to do, code word length 3. I can't add anything else to this branch, so I need to create a new one with 2. But because I don't stop there, I have to find length 3, then I just add like 0, right? And then what that's going to end up with is I have 0, 1, 2, 1, oh my god, 2, 0, 2, 1, 0, 2, 1, 1, 2, 1, 2, and then 2, 2, 0. And that's my code words, essentially. This would be a very standard instantaneous code there. And me, personally, I prefer the tree method. I think it's easier to pick up on mistakes later. But, up to you, right? But you get the same thing. Very, very cool. Very, very slay. Hopefully everyone's doing well. Alright. Moving on then. Minimal codes. So, also just like to remind everyone that, Just like to remind everyone that these are recorded, so you guys can see this later. And just another reminder that we have part 2 tomorrow at 11 to 1 as well. Yes. Please come to our seminars. Yes. Anyway, minimal codes. We are interested in making code words as short as possible. Why? Because it is more efficient, right? So more specifically than just make code words as short as possible is to look at the average code word length, right? Because if that is the smallest that it could possibly be, then we know that we have the minimal code, the most efficient code, right? So let's just go through and pull out the whole definition. So the whole definition, we have an equation for the average length, equation for the variance. The variance doesn't come in as much, but still important. It's just derived from the variance formula that we're very familiar with. But average length, very, very important to know. Okay, so let's go down here. We say that a uniquely decodable code is minimal with respect to its probabilities if it has the minimal average length. So as long as we minimize this, we're good, right? Okay, so going off of these code words, say I had these, right? With probabilities 2/3, 1/6, 1/6. Using this equation here, we can actually find the average code word length to be 5 on 2, right? Because we're just timesing these by the length of this, right? So 2 on 3 times 3, 1 on 6 times 1, 1 on 6 times 2. Perfect, right? However, what we can do is we can say, oh, this code is actually not minimal. For example, if I consider these code words, then I actually get a smaller average length, this average length being 4 on 3. I would like to say, I'm not really sure if this is the minimal code exactly, if this is the minimal code, but it goes to prove that this is not the minimal code, right? That the first one is not a minimal code. Yeah. So hence, from here onwards, please assume that the source symbols are rearranged in non-increasing probability. Okay. Let's go through some theorems. I'm just going to scroll down so that all of it's on one page at once. Minimal codes. So the theorem is that the lengths are going to be in increasing or non-decreasing order. The length of the last two have to be the exact same. And before I jump into the other two, let's just show that we've been kind of doing these already. So let's go back up to an example that we've been having. What is the valid code that we had? Yeah, okay, so these, right? If I have 1, 0, 0, and 0, 1, you can see that in terms of length, these are in non-decreasing order, right? Because this is length 1, this is length 2, this is length 2, increasing, right? On top of that, these last two codes are the exact same length. One thing that I'm also going to take note of is note how the last two codes, they're exactly the same except the last bit is different. So instead of a 0, this is 1, right? And we're going to notice that that's exactly the same for the previous example as well. If I just go up to this, get parent, where's a valid code? There, okay, cool. Similarly here, I have 1, 2, 3, 3 as my lengths. That is also non-decreasing. Our last two are the same length, and on top of that, our last two code words only differ in their last bit, right? So, slay. Okay, going back to... Sorry that I kind of just jump between slides. Apologies about that. Where am I? I do not know. Where am I? There it is. Okay. Yep. And then we have this thing where it's like, okay, by the way, if C is binary, then this sum is going to end up with us having 1. This is actually just the same as our previous thing here, where we just had this. It's just written in a different form, but please remember, note that that's just like the same thing. Literally the exact same thing. Where instead of the inequality, it's going to be equal to 1. Cool. So put slay. So let's take a look at this really quick, just to prove that last statement there. Consider the binary code words 0, 1, 0, and 1, 1, which correspond with these probabilities, right? We can see that this is very much a minimal binary code. Why? Because, again, increasing order, so 1, 2, 2. The last two are the same length, which is 2. They are instantaneous because these two only differ in their last bit. And it is binary because half plus a quarter, that's going to end up with 1. Alright, so it satisfies all 4 dot points, minimal binary instantaneous code. Alright, hopefully everyone's good with that. Just checking that no one has any questions, super slay. Okay, moving on to Huffman's algorithm. So, Huffman's algorithm is a method to find the instantaneous minimal code for a source. Right? Instead of going through all of the steps like kind of here, I'd rather go through an example. Right? Okay. So let's just go through an example. Okay. Using Huffman's algorithm to construct an instantaneous minimal code for source blah with respect to probabilities. Okay, yeah. Great. So first things first, what I'm going to do is, because I'm going to be constructing kind of like a table or a tree. That's the word. A tree. Yes. I'm going to write these all in the column at the side. And what I'm going to be doing is, I know that this is going to be radix 2. So what I'm going to be doing is I'm going to be adding the last two probability together. And remember that in this code, in this course, we're just basically setting this higher. 0.3. I should do these in like dots just so that you guys can see which one I'm actually adding together. Again, same deal, going to be adding the last two. 0.6, 0.4. I just like to note that I put this 0.3 above this one because we're setting everything higher, right? However, that does not go higher than 0.4 just because 0.3 is not greater than 0.4. And then these two we get added together into 1. What we're going to do here is we're just going to go, okay, well the top is going to be 0, the bottom's going to be 1. 0, 1, 0, 1, 0, 1. And this can become our code, right? So if I was looking at the one that corresponds to 0.4, then I can say, oh, if I just follow this, it's going to be 1, right? So that's going to be 1, S2, S3, S4, 3, 2, 1, right? The one that corresponds to 0.3, I'm just going to follow it. It's going to be 1, 0, 1, right? And I can do the same with the other codes, right? And this is going to basically be our construction of our instantaneous minimal code, right? And I think if I scroll down, yes, there's an illustration of all of this. Super perfect slide. All right. Hopefully everyone's okay with that. The big thing to keep in mind, and honestly where I see people making mistakes, is just like making sure to place this high instead of placing it at the bottom. All right. Okay. So moving on. Okay. As mentioned before, Huffman's algorithm gives us a code with a minimal average code word length because it finds us our minimal code. So I don't want to say his name because I don't know how to say his name. I don't know. Anyway, this theorem, yes. The average code word length is the sum of all the child note probabilities. So if I go back and I look at this example, right? I might look at my drawing instead because, haha, my drawing is better. No, I'm kidding. Anyway, we see how we added for this, so this becomes a child node. This also becomes a child node here, and then we also have one here that's a child node as well, right? So what our theorem is essentially saying is that our minimal average code word length, min length, is going to be the sum of all of these child nodes, and you guys can see very, very clearly that's going to be 1.9, right? That's it. That's essentially all there is there. Yes, 1.9. Alternatively, if you say forget that, because that is at the end of the day a little bit of a shorthand, then alternatively what you could do is, if I scroll back up, is you can go through and go, okay, this is length 1, 0.4, then I have 1 times 0.4, plus 2 because 0, 1, 2 times 0.3 plus 3 times 0.2, so on and so forth for all of the codes, and then you should also be able to get 1.9 from that as well. Right, this theorem is essentially just a shorthand. Cool, so it's like, okay, yeah. So we can also use Hoffman's algorithm for any radix, more than just 2, right? But the problem with this is that we very much need to keep in mind dummy symbols. So it's like, with the binary case before, we could very easily, this is the binary case before, with the binary case before, we could just merge the last two. Always. Just always merge the last two. Right? The problem with this when it comes to radix, when it comes to higher radix, is that we might end up getting we might not end up getting the minimal code if we don't use dummy symbols. Right? So just to I'm gonna display this later, but this is essentially the reasoning behind it, right? So we add in dummy symbols with probability 0 so that the number of symbols is like kind of correct, right? Okay, let's do this with an example, right? Okay, so 0.3, 0.3, and a bunch of 0.1s, right? And if I just look at this really quickly, I can say, oh, okay, because I'm with radix 3, I actually don't have the correct, number of symbols, right? So what I'm going to do is I'm just going to add a dummy symbol with probability 0. And now, because I've added my dummy symbol, what I'm going to do now is I'm just going to be using my Huffman's algorithm as I was doing earlier. Except instead of constructing the last 2 branches, because it's radix 3, I'm constructing the last 3. Right? So these last 3 added together is going to be 0.2. And placing it high, it's going to be up here, 0.2. Right? Everything else I'm just going to write down here, just so I can keep track. Ooh, why are you not loading? Stop, do this properly, please. Thank you. Okay, great. That's the first addition. Same here, and when I add the last 3, they're going to leave me with 0.4, 0.3, 0.3, and then finally I can add these to be 1, right? Where these are my child nodes. And essentially, when I get to this point, if you ever mess up and you go, oh, I forgot to add a dummy, or I added the incorrect amount of dummies, then you just need to remember that all of these branches should be very much 3, right? Or similar to whatever radix you're working with. It's very easy to just kind of see, oh, did I mess up with the dummy symbols, right? But essentially, from here, again, adding the 0, 1, 2, 0, 1, 2, and then following your tree just to find the code words, right? And I think, yep, yep. Okay, I think, yeah, we have this here. Which essentially is basically the end of that question. And very, very similarly, we can use the theorem from earlier, from the child nodes, just to be like, okay, when I add up the child nodes, that's 1.6. Alternatively, if you forget, it's okay to do it manually as well, using the longer calculations. But you'll get to the same thing. Okay. If everyone's alright with that, I'm going to jump into extensions then. So extensions. Sometimes compressing symbols is not possible, or it has no effect, right? This is where we bring forward extensions. So, if you want to think about compressing a symbol that isn't possible, consider a source with 2 symbols S1, S2. And with these 2 symbols, if it's 1, 0, A, B, whatever it is, we can always assign this as 0 and 1. And hence, no matter what congregation that I have of these, S2, S1, there's always like a specific way to write that out. So it's always an average length of 1. And this is no better. This is absolutely no different to the fixed length codes that we were doing in chapter 2, right? So instead, okay, what are we going to do? We're going to use extensions and see if we can change this up. So, for example, if I was to extend this, encode multiple symbols at a time, yep. So, yeah, this is just the extensions definition that we got from the lecture notes. But say I had a source alphabet of A and B, right? Well, then naturally, if I was to extend this, so S2, I would get A, B, B, A, B, B. All the possibilities where it is length 2, right? And these probabilities can be easily found for that, because naturally AA is just going to be 7 on 10 squared, right? AB, 7 on 10 times 3 on 10, all of that, which gets us these probabilities. Very easy to calculate, right? However, if I was to run this through Huffman's algorithm, then we'll naturally obtain these, right? And just to prove that, if I have 49, 21, 21, and 9, this together, that's going to be 30, 49, 21, 51, 49, 100, right? 0, 1, 0, 1, whoa! Am I number 1 or 8? What? Anyway, sorry. Got distracted for a second. Okay. What? I have no idea what's happening. Okay. Anyways. If we follow this Huffman, we're going to end up with these code words, right? Okay, yeah. So, however, naturally you guys can see, this is going to be a child node, this is a child node, this is a child node. And remember that all of these are on 100. So 30 on 100, plus 51 on 100, plus 100 on 100. That's going to leave us with 1.81, right? That is a lot better than, like, 2. Which was what it would have been if we didn't use this extension. If we just, say, had symbol 1, 0, 0, that would have just been an average code word length of, like, 2 for these, right? But now, suddenly, using extensions, we can have a better code. Yeah, and that's essentially here. Right? We think we've achieved compression this way, where we just consider extensions super slay, super cool. This is the same slide twice. What? Okay. And if everyone's all good with that, this is Markov sources. Okay. So far we were able to take advantage of source symbol probabilities in order to reduce average length of code words, right? But we can actually do even better compression sometimes, and that's with Markov sources. So we're going to use a transition matrix and control sources. Yeah. Oh my god, I've said Markov sources so many times. Anyway, yes, we're going to use a transition matrix, right? And essentially what this is going to do is, when we are encoding, the ith column shows the probability of symbol occurring right after si. And this might not make any sense right now, but yeah, I'm just going to go down to this. This might not make any sense right now, but I'm going to go through an example of this with a question, right? So hopefully everyone is willing to do that. Okay, with this example, right, we have a Markov source bar with a given transition matrix and an equilibrium vector, right? And what I'm going to state really, really quickly is I know that the first column, 0.3, 0.5, 0.2. So what we're essentially saying here is that the probability of S1 after S1, so S1 after occurring S1 is going to be 0.3, whereas the probability of the next one after an S1 is supposed to be 0.5, and same with S3, that's going to be 0.2. That's essentially how we read this, right? And the probabilities here, similarly, the probability at all of S1 happening, well, we just read the very first one, which is going to be 56 on 145. The probability of S2 occurring is 53 on 145, and the probability of S3 is 36 on 145. Right? That's essentially what we're reading of here, and that's written down here. Yeah, that's just essentially written down here as well. Right? Cool. Super slay. So essentially, it turns out that we can actually use Huffman coding to take advantage of Markov sources. So let's actually just go through this with some. I'm just going to scroll down with all of the examples here. But length is basically still, keep in mind, the same as what we were doing for length earlier, right? Very much the exact same. Okay, but let's talk about some encoding strategies. So, when we're trying to encode, say, something like this, S3, S1, S1, S2, it's written down here, but I'm going to read it out as well. You're going to end up with basically 3 chunks. This is hard to read. Basically 3 chunks of Huffman codes. 4, get bragged, 4. Right? And that's going to be half 1, half 2, half 3, half 4. Not half 4, half E. Right, and the very, very first one, S3, we always encode, whatever the very first one is, we always encode using half E. Right? From there, the next ones that we encode, so S1 is occurring after S3, so we go to half 3, right? And then S1 occurring after S1, so we look at half 1. S2 after S1, we look at half 1 as well, right? So we're always essentially looking at the corresponding one of the one before it, right? And we'll do an example of this, no worries. But, yes. Ooh, I don't remember what paper we got this from. But, yeah, so looking at this question, we were given the transition matrix and the equilibrium, given blah, 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 blah. Construct Huffman codes for the Markov source and find LM, its average code word length, right? So, to construct Huffman codes, what we're going to do is we're just going to be looking at all of these columns here, right? So, I'm just going to do one example by myself really quickly. So, if I was looking at the very, very first column, which is going to be my Huff 1, that's going to be 0.6, 0.2, 0.2, and obviously we know how to do this now, so putting in 0.6, that's going to be 1, and then using that construction, I have 0 as my code word here, 1, 0, and 1, 1, right? These are my constructions here. And I'm going to do this with essentially all of these columns to get half 2, half 2, half 3, and then if I do it here as well, I'm just going to get my Huffman E, right? And I think we have, yes we do, yeah. So if you guys want to see what that construction looks like, it's going to look something like this. We've circled the chart notes for you just so we can make it very easy to find the average code word length later. Right? Super duper slay. But yeah, from these codes, we're going to end up with these code words. So half 1, 2, 3, and E. And if I was to find the average lengths, well then 1.4 from here, 1.6, but just by adding the chart notes, right? And then finally, what this ends up with is our length here, right? Super slight. Where these lengths just come into play here. How we use that, yeah? Okay, super cool. But now let's actually go to the second part of the question, which I know is a scroll back now. But we want to encode S2, S1, S1, S3, and then decode something else as well. I think I've written it out here as well. Yeah, I have. Okay, so to encode S2, S1, S1, S3, first things first, the very first symbol I always read off of half E, right? And that's going to be our second one, which is going to be 0, 0. So I know that this is going to change to 0, 0. Okay, the next symbol is S2, which has occurred after the second symbol is S1, that has occurred after S2. So we're going to be looking at Huffman 2 now, and we're looking at the very first one, which is going to be 1, right? And the next one is S1, which has occurred after S1. So this is going to be 0. And then S3, that has occurred after S1. Again, that's looking at Huffman 1, and S3 is 1, 1. Right? And that should be our, if I scroll down properly, yeah, that should be our encoding there. Right? Super slight. So yeah, just make sure you're looking at the previous relevant Huffman. Alright, to decode. To decode, remember that our first symbol always has to come from Huffman E. So, which here corresponds with the first bits of our decoding? Well, it's going to be 0, 1, right? So then my very first symbol is going to be S3, right? Which we've written out here. Now, what are we looking at after S3? Well, because we did S3, we're looking at Huffman 3, right? And then what we find is we can do 1, 1, right? 1, 1. And that will correspond with another S3. Similarly, we look after that, so we can look at these 3 symbols now. We have a 0. So hence that's going to be S2. right? Now we need to look at Huffman 2 now because we've changed symbols. So we look at this one or this 0, this 1, 0. We're going to end up with S1. And then finally, when I look at Huffman 1, I see 0, and that's going to be S1 again at the bottom. And then that's going to be my final decoding, right? Hopefully that is all good. Yep, okay. Now, I think I have an exam question. Oh my god. Okay, but this is taken from 2019. So, Markov source has this transition and this equilibrium. And this is already very, very similar to what we were already doing. Part A is basically the exact same as what we did already, so I'm kind of just going to skip it. This is what that encoding will look like, right? Okay, using these Huffman codes to decode this, right? So again, always looking at half E first. I know that I see two zeros at the front, so I know that my starting is going to be S1, right? And then looking at Huffman 1, I can see, okay, 0, 1 matches, so it's S1 again. What about the next 4? Okay, 0, 0, S2. So now I need to look at Huffman 2 to encode 0, 0. I have S3. And then I have 1, 0 at the very, very end. That's going to be S1. And that's my final decoding for part B. Right? Very simple, very easy. And I'm just going to write that over here, just so I can use the space again. S1. Okay. But the reason why I included this, because this is so far A and B is everything that we've already done. The reason why I included this question is because of part C. So using the Huffman codes from part A, suppose that a message is encoded with 3 bits exactly, one of which is 1. Find all such messages that are possible. Right? So first things first, we can very clearly see, if I was to have 3 bits, exactly one of which is 1, you guys can already know that there's kind of like only 3 possibilities of what it could be, and that's going to be these 3, right? So how can I decode these? Well, if I was looking at half E, if I have 0, 0 at the beginning, right, where I'm looking at S1, I can go, okay, well, for 0, 0, there's a possibility that it's just S1 at the beginning. And then if I have S1, oh, well, perfect. S3 is this, right? So 0, 0, 1 is just S1, S3, right? And that's that encoding done. So I'm just going to cross that out. Okay, next one that I can probably go. 0, 1, 0. Okay, well, 0, 1 is going to match up with S2. So hey, what if it's 0, S2? And then we look at Huffman 2, and is there anyone that has a 0 at the end? Well, yes, there's S3. Right, so that's another possibility that we can code up there. And now finally, we're looking at 1, 0, 0. So 1, 0, 0. Is there anything that starts with 1 or 1, 0? Well, yes, it's S3. So cool. Looking at the last one, is there anything that is 0, 0? Unfortunately, yeah. Unfortunately, there is no 0, 0 here. So there is no valid match here. Right? Just because you guys will see, if I have that extra 0 here, then I have S1, and then I need to look at Huffman 1 for a singular 0, that doesn't exist. Right? So we actually can't decode 1, 0, 0. However, we can decode the other 2. So let's just cross that out. So find all messages M, well, my messages are going to be S2, S3, and S1, S3. Right? And that's it. Super cool, super slate. If everyone's cool with that, just checking that we're all good, we're all alright. Okay, cool. Arithmetic coding, right? So now let's turn to a completely different type of compression codes, and we're going to be talking about 2 in this particular case. I think it's going to be arithmetic coding and then LZ78 codes, right? But arithmetic coding remarkably encodes any message to a single real number. And I'm just going to scroll down so I have the whole thing on the page. There we go. Okay, so what we do is we have a source symbol where the very last symbol has to be the stop symbol. That stop symbol is basically going to tell us, oh, okay, we've finished encoding, this is done. We don't have to do anything else, right? But what we do is, actually, I'll probably demonstrate this with an example. Yeah, probably demonstrate this with an example. So, with this encoding, one way to track for encoding is just to write down everything start and then width, right? So if I wanted to encode CAB with a stop, then I'm gonna go, okay, on a line 0 to 1. Ooh, that is not 0 to 1. 0 to 1. First probability of A is going to be up to 0.2, which is going to be A. Then the next is going to be side 0.4, so that's going to be up to 0.6, which is B. 1, which is 0.7, C, and then the rest is going to be my stop, right? Something like that. And then how to encode it. So I think we actually go through this kind of one by one. Yeah. So to encode, you need to keep track of your start and your width, right? So I like to make a little table for this just because I can keep track of everything, and that's also how the lecture notes does it as well. But if I'm starting with C, I might just need to keep. If I'm starting with C, 0, 0, 0.2, 0.6, 0.7, and 1. If I'm starting with C, which is in this section, then you guys can know, okay, well, easily the start is 0.6. And this width of this interval is 0.1, right? And then what we're going to do, move the 0.1 here and here, and we're going to times it by the next section. So the next section is A. Drawing this up really quickly again. Probably should have done this before, but oh well. If I have A, you guys know that the start of A is going to be 0. So we times this by 0. That gives us a new kind of start. But the width of this is 0.2. Times that on, right? And then same deal, this width is going to come down to these two spots, right? Here. Super slay, right? We try to use colors to kind of just show you what follows on. But yeah, with B, we know that's going to be 0.2 at that starting. And then this has a width of 0.4. Which will result in this. And then finally, we need to code in our stop to tell us to stop, right? And that's going to start off at 0.7, and it has a length of 0.3, right? And then we end up with these two funny little numbers. And what these funny little numbers mean is that this is a valid encoding for CAB stop, and it has a width of this. So anything plus minus this, 0024, any number that falls into these conditions will encode for CAB stop, right? So for example, anything in this subinterval will be the correct encoding. For example, the easiest one will be 0.61, right? And that is arithmetic encoding, right? Hopefully that is all good. But alternatively, let's decode, right? So we have to decode 0.08. Essentially, what we're trying to do is we're trying to trace back the encoding process, right? So the first things first is we're going to go through, I'm going to draw this again just because, like, I very much like to read off of this when I am encoding and decoding. 0.6, 0.7, that's going to be A, B, C, and stop. Okay. To decode 0.08, first we need to identify which interval this actually lies in, right? And we can see, okay, well, it lies in A, right? And we're going to basically rescale this. So if I rescale this, if I also make this like the same as this, right? Right, 0 to 0.2. So hopefully you guys see what I mean by, like, we're just rescaling it. Oh my god, this is so ugly. No. Please. Okay, a little bit better. This is as good as it's gonna get. Rescale this so that it becomes 0, 1. And we know that 0.08 lies in this interval now, right? And then we basically repeat this until we hit the subinterval for the stop symbol. And I think we write this out, actually. Yeah, we do. Okay. So this is essentially what our working out is going to look like. So you're going to rescale the intervals until we get to the stop, and until we reach, until we get to the stop, right? So originally it's 0.08, and we know that that interval is between 0 and 0.2, right? Interval width is 0.2. We know that the symbol that corresponds to this interval is A. Perfect, great. Moving on. Our next calculation, if we're going to rescale, is it's our scale number minus the start divided by the width, right? So this minus the start, which is 0, divided by the width, 0.2. And that's going to end up with 0.4. And now we know that this interval is going to lie between 0.2 and 0.6. which corresponds with our symbol B, right? And then next things, we do the exact same calculation. So using this, we minus the start divided by the width. We're going to get 0.5, which lies in the exact same interval, which is a B again. Doing this calculation again, we're going to get 0.75, which is our stop. And hence, we have decoded this as ABB stop. Right? Super slay. Okay, cool. Yes. And that is basically arithmetic coding. I think the tests this time did a pretty good job of kind of displaying that. So if you need extra practice on that, that's super cool. From what I've seen from the 2017 to the 2019 papers, which are the most recent ones that we have access to, there's not a lot that goes like very, very in-depth, very technically difficult, very conceptually difficult with arithmetic coding. But I haven't taken a look at anything privy to 2017, so maybe. But yeah, this I feel is pretty stock standard and also is pretty simple to code as well. Python is very, very good for this as well. But LZ78, if everyone's all cool with that. Ooh, we are doing pretty well for time. That's so cool, guys. Oh my god. Yes. Another method of compression coding is using dictionary methods, which is very, very completely different to everything that we've also done so far as well. But one of the most popular ones is LZ78, which basically works on building up a message from what we already previously had, right? And I'm just going to scroll down to the method, right? Take a quick read of it if you would like, but I'm going to probably, wait, hold on, there's one more. Yeah. I'm gonna go through this in an example, right? Okay, so cool. So this is very, very, this is kind of what you would expect from like our tests and all that, but use this to encode the message, yeah, right? Okay, so we've started this stuff table off, and I'm actually gonna complete the table on this slide probably, but, you guys can very easily see, well, the very first, symbol, A, we obviously have just started, so we can't construct it off anything previously. So I'm going to say that 1 is A, right? And then how I say this output is going to be 0. Why? Because it's the zeroth symbol plus an A at the end, and nothing plus A, right? So that's A gone. Right, and then now I consider B. B, obviously, I can't construct from anything previously, so it's also its own thing. That's going to be 0B as well. 0 because, again, we're constructing it off of the very first one, right? Not off of this. If it was 1B, then we would expect AB, right? But that's obviously not the case for this, right? Take off the B. Next, I want you guys to consider there's a BA here, right? Since there is a BA here, well, we can say it's BA. This is the same as the second symbol, so B plus another A at the end, right? So second symbol plus another A at the end, right? And we'll basically continue this for the entire process. I might just scroll down just so we can see that coming through. Yes, okay, cool. And then this will be the final coding. So that's essentially what I was trying to do earlier, just by displaying it to you guys. A, B, and then BA can be composed off of previous ones, right? Second we got to C, that was unique and its own thing, right? Just wanted to make sure that you guys have the output correct. I know that was something that I was kind of like, what is happening before? And to decode, we're basically reversing this entire encoding process, right? So I'm going to give us an example of that as well. To decode, we just reverse the encoding process. Rebuilding the dictionary entries, please take the following steps, and I'm just going to scroll out and let you guys take a look at this. Basically, we're looking at the idea of appending and concatenating, and that's it, right? So, let's decode all of this. What does that end up with? Well, naturally, we're going to start off with 0 being nothing, right? Dismiss the table, I'm kind of not working with it. And then our very first symbol, well, it's going to be defined by this. 0B, well, if I append B to 0, that's going to end up with B. If I append 0 by A, I get A. And same with 0C, right? And that's my first three brackets out of the way. The next one is I need to append the second symbol with B, right? So I append the second symbol with B, that's going to end up with AB. Next, that results in the first one appended with a C, so that's BC. 6, I'm appending 5 with a B, so BCB. 7, I'm appending 4 with AC, I get ABC. And 8, I get 6 appending with A, that's BCB. A. Right, and that's all of my symbols. That's me reaching the end of here. And finally, my encoding is just going to be the concatenation of all of these, which is BAC, ABBC, BCB, ABC, BCBA. And that would be my final encoding. Right. And if I just scroll down to all of this, you guys will see that that's exactly what we get here. Right? Oh my god. So slay. So summary from a really quick summary from this chapter is essentially there are a lot of ways to compress code. But things that we consider when we're compressing code is that we have to consider the length, right? Always considering our minimal length. And on top of that, we have a lot of ways to compress. So we have, for example, Huffman's algorithm to find that minimal code. We have the respective theorems within that. We have the concept of extensions. And then we have the concept of Markov sources. And that's basically our big thing from this, right? And what I might do is I might just hop to the 2019 exam and give you guys an example of what I see is pretty common from the first 2 examples, right? Where where some of these concepts come into play. So what I've noticed from the 2019-2018 exams is that topics 1, 2, and 3 are essentially just assessed in the question 1, right? And question 1 in both 2019 and 2018 is just a kind of true or false, right? So valid ISBN, that is from our chapter 1. That is just us using this theorem here to check that it is valid. If it is valid, it'll satisfy this. Send I code, that is from our chapter 2 or 3. Huffman code, where we can just prove that. Markov, which is chapter 3. And then arithmetic coding, which is also chapter 3. Right? Very, very similar and basic concepts that come through here. But a lot of these questions we kind of did within the seminar, so I'm not going to kind of repeat and go through it again. If anyone has any questions, that's super cool. But that is actually the end of it. End of the seminar. That is chapters 1, 2, and 3. So, I'm hoping that all of you guys kind of at least took a few things from this. Reminder that tomorrow is going to be topics 4, 5, 6, and 7. That's going to be hosted by wonderful Christian and Ronald, so please come check that out as well. Just a reminder that these are recorded, so if you guys are like studying at 2 a.m, you guys can always come back to this as a little bit of a basis. Yeah, so if no one has any questions, this might be the end of that now, right? Just one thing that I'm really going to quickly note is when it comes to Huffman, it's going to be, we're going to come back to the concept of average code word length throughout the next few topics as well. But yeah, good luck studying, everyone. Hopefully we slay the final exam. And yeah.